everybody. Today we're going to look at topic 11, which should be read by you in the book, pages 261 to 271. This is going to be our discussion of scientific processes that you've pretty much already learned. There's going to be a couple new things, and we'll talk about those, but you have pretty much already learned what these are. We're going to start with significant figures, and as you know already, a significant figure is a number that is meaningful in a measurement. And you know, in a measurement, there are the estimated numbers and the actual measured numbers, and all of those are part of the significant figures. One of the things, however, that can be a little dicey is those zeros. All numbers except 0 are significant. Some zeros are significant and some zeros are not significant. And so we need to think about, well, what makes something not significant? So we are going to take a look at what makes them not significant. I want to see if you remember anything. So please go back to the chat and go ahead and comment in the chat. What are the rules for significant and non-significant zeros? Go ahead and write down what you think those correct rules are. Okay. So, correct rules for when a zero counts and doesn't count. If the decimal point is written in between other significant figures, it does count. So, if it is a 0 in between others, then the zeros count. If it's after the last number, then it does count as well. So, zeros at the end, as long as there's a decimal, those zeros count as significant digits. However, zeros at the end with no decimal place do not count, as are zeros that are leading zeros. Leading zeros never count. So you need to be able to distinguish between those, and hopefully you got that right in the chat. So let's go ahead and take a look then at what do we do with the math of correctly using our significant figures. So let's remind you that when we are multiplying and dividing, the number of significant figures of the answer should be rounded to the least number of significant figures of the numbers in the problem. When we are adding and subtracting, then we switch to decimal places and we are rounding to the least number of decimal places of the lowest decimal places in the problem. Okay, so let's see if we can figure this out. In the chat, please tell me what is the correct answer for the density of the rebar in this picture. It might be a little bit hard to read, so you can see that the rebar mass is 69.658 grams. The final volume is reported as 22.4 milliliters, and the initial volume is reported as 13.5 milliliters. So go ahead and do your calculation. Please remember to use your math and rounding for significant figures and decimal places correctly. And when you have your answer, please go ahead and put that in the chat as well. Okay, so hopefully we got our chat done, and we'll go talk about those in person. If you are a person who is not in person with us, you're an asynchronous person today, then when we do the final discussion at the end of this activity, then I'm going to ask that you put in your discussion pieces for how do you know zeros are significant or non-significant, and your answer for the density question there as well. So keep that in mind. You're going to need to add those two to the discussion question at the end. Just a little reminder here, the metric system is still very much in play. We're going to be using all those same units like you're used to seeing, so no big surprises here on that. Some prefixes that we have used before. Mostly what you're going to see is that we will use kilo, deci, and centi most often, but those are the other ones so that you know about them and can recognize them when you see them. All right, so we get to IB terminology, and at some point in every IB course it becomes obvious that IB uses some different terms than we are used to seeing it. So I'm going to ask that you start a set of flashcards for all the new terms that you are going to use, because flashcards, while you might think are old-fashioned, will come in very handy when you are studying for things. So it's time to start a set of flashcards, and the first thing that you're going to put on your flashcards, while you might want those unit labels and those metrics, you might want significant figures in your flashcards as well, but the one that I want you to add right now is called the liter, because IB does not use the terminology liter. Instead, IB uses the terminology 1 decimeter cubed, so 1 dm3. And so you're going to want to remember that one, because that one's going to come up a whole bunch of times, and it will be very confusing for you if you don't remember that that is equal to 1 liter. Now, what I have behind this picture here is a link to a site that has IB chemistry flashcards. Take advantage if you want to take advantage of it. I believe these are free. Otherwise, you can make your own, certainly. All right, so the next thing that we need to pay attention to is uncertainty. And there's going to be, this is going to be new terminology for you. And so this is going to be two types of uncertainty. We're going to express them both the same way, but we're going to do them slightly different based on the type of measurement device we have. So if we have a digital scale like this digital mass scale, then we are going to take the minimum reading that the scale can read. So you'll notice that the top picture can read to the first or the 10th place, so 0.10 grams. And so the measurement for the top scale can be written as 14.8 grams plus or minus 0.1 gram. And the plus or minus 0.1 gram, that's the uncertainty. And so that, what is that saying? That's saying that we can be sure of this measurement between 14.7 grams and 14.9 grams. So if you were to look at the scale at the bottom, you would notice that that scale is showing nothing is being measured, number one, but we would be able to show this uncertainty as first the measurement 0.00, followed by plus or minus, then 0.01 grams. And I forgot to say this should be written as 0.00 grams plus or minus 0.01 grams. And that would be how you show the uncertainty for that second scale. Now, things change a little bit when we don't have a digital scale. Instead, we have an analog scale like this scale that you see in front of you. And so if you take a look at how long is the blue bar, this is looking like it's coming in right around 31.0 centimeters. And so in the red down below, it says, remember, the uncertainty, which is the measure of random error, is half of the smallest division. So in an analog scale, we would say that the smallest division is to the ones, so half of that is 0.5. So you'll see, as we see up above, the measurement is written correctly with the uncertainty as 31.0 centimeters, parentheses, plus or minus 0.5 centimeters, close parentheses. Now, you might wonder, should I show parentheses? Should I not? It is your choice to decide whether or not you're going to show parentheses. If it makes it clearer for you, then show the parentheses. Now, this is all how we are going to measure and how we're going to show our measurements. All measurements are uncertain to some degree. Okay, what depends here is how repeatable are they, so precision, that's another flashcard word, and how accurate are they, or in other words, how correct and close to the true value are they. And those two words should be added to your flashcard list right there. Okay, so this all leads us to, well, what kind of errors are our uncertainties trying to describe? And it turns out the uncertainty is trying to describe random error. These are errors that happen due to estimation. So they would have equal chance of being high or low, and we can reduce random error by averaging measurements and by taking three measurements and averaging them together and coming out with an averaged answer of the measurement. Systematic error, on the other hand, is something that might be due to an uncalibrated machine, poor installation, in other words, a faulty experimental methodology. It might be an incorrect measurement technique. Remember, we have a way that we measure graduated cylinders. We might look at a color the wrong way, or we might not take as good care with measuring as we thought. Those are systematic errors that can only be changed by changing our experimental design. Okay, for your discussion that is going to happen next that you can do in Canvas, you are going to respond with your name. Well, your name will be on it, excuse me. The name of the measuring device, the actual measurement, followed by the plus or minus uncertainty, of course showing it to the correct number of decimal places, followed by units in the correct places. So please respond in the discussion with the 7 different measurements that you see before you and figuring out what those correctly are. Once you are done, please also respond to one other person as to whether or not you believe their answers to be correct. Thank you, everybody.